Okay, so hello everyone. Okay, so this is the first IC seminar in this semester. So today's speaker is Linn Eriksson from the Lund University. She took her PhD in this spring, and her supervisor was Anders Johansen. I think he gave a talk. He gave a talk in our seminar in the last fall about the Accretion and transformation theories. And her work also relates to the pebble accretion, and I think she will talk about relation about the pebbles and transceiver in today's talk. And she will, as written on this slide, she will move to the New York from the next January. And now she is visiting us, and she stays for 1 more month. Yeah, so if you have any questions, you can discuss here in the next this month. Okay, so let's start the talk, please.
Okay, thank you. Okay, yeah, so I'm Lynn, I'm here visiting, and the topic I will talk about is basically what I've been working on during my PhD, which is this saga of planetesimal formation and planetary gap edges. And it's been done in collaboration with all these nice people written on your slide. For example, also David and Claudio here from Zurich. And it's also something that I will continue to work on during my postdoc in the US. So since it's a department seminar and a broad audience, I figure I'll just start with some very sort of basic introduction to planet formation. So of course, the planet formation process takes place in protoplanetary disks. And the sort of main goal of the research field is to understand how we go from having like a star in a disk to having the plethora of planetary systems that we see today in observations. And all these planets have hugely varying properties. And we also have many planetary types which we do not have in our own solar system, like, for example, the hot Jupiters up here, or the super-Earths. And the planet formation process is a multi-stage process, which starts with these tiny micron-sized dust rings embedded in the disk and ends with fully formed planets. And it spans something like 14 orders of magnitude in size and roughly 30 orders of magnitude in mass. And although my work sort of touches upon a lot of these steps in the planet formation process, I focus mostly, I would say, on the first 2 steps. So that is the steps from dust particles to pebble-sized particles, which is like millimeters in size roughly, and the subsequent steps from pebbles to planetesimals. And I will also talk a bit more about those soon. But I figured I'd start with just saying a few words about protoplanetary disks. So there are these thin structures. They're roughly like 99% gas, 1% solids, and they evolve with time as matter is accreted onto the central star. And we can try to get a feeling for how long these disks stay around. So here is a plot of the disk frequency. So it basically tells you for a stellar cluster, a young one, what is the fraction of these stars that has disks around them as a function of the cluster age. And then if we look at 50%, we find that the average lifetime is somewhere around 3 million years. So that's basically the time we have to form our gas giants, because after that, there is no more gas around, so no more planets to form. And the most sort of common model for the evolution of a protoplanetary disk is what's known as the viscous accretion disk. So in such a model, accretion onto the star is facilitated by a transport of angular momentum radially outwards in the disk. And this is supposed to occur because of some viscosity or turbulent process. Now, lately, it seems that there are more and more evidence suggesting that actually this accretion happens because of some MHD disk wind. However, these models are fairly new and rather complicated. So even though we know that that's probably the case, most people still stick to the well-understood viscous accretion disk models, which is what I'm going to use as well in my work. So here I show you an example of such a disk, say with the surface density versus major axis. And basically with time, the density gets lower and lower in the inner disk. And we also see how this disk expands in the outer part because of the outwards transport of angular momentum. And then when the disk disperses, this usually happens because of photoevaporation. So here I've put in some constant photoevaporation rate to make sure that the disk disperses at 3 million years. Okay. So then let's move on to the planet formation process. So the first step then is the step from dust to pebbles. And this occurs via mutual collisions. And people use laboratory experiments to figure out sort of what happens in which collision. And this has shown that we basically get either sticking, bouncing, or fragmentation. And this model here is a model from Güttler et al. So it's probably the most common collision model out there. And it shows basically for it shows the outcome you get in a collision for a certain mass of the projectile and the collisional velocity. And here is the model for porous particles. So they separate between equal-sized particles and unequal-sized particles. And basically what this shows is that if you have a low collisional velocity, like here, then it's very likely to do the sticking. But the higher the collisional velocity, the more likely it is to lead to fragmentation. And it also shows that if you are of smaller particle, it's more likely to lead to sticking. Okay, so what you do then is that you take this collisional model and you put it into your simulation. So here I did that for a sort of viscous accretion disk model. And then what you basically find is that you very quickly form roughly millimeter-sized particles in inner part of the disk. And thus, the further out from the star you get, the smaller the particles that you create are. And it also takes more time to form these millimeter particles the further out you get. So like at 20 AU, you might form them already after a few 10,000 years. But if you go to 100 AU, you need a few 100,000 years in order to fully coagulate them. Okay, so that's sort of the dust to pebble step. Then we can move on to the next step. So how to get planetesimals. And we saw in the last plot that we cannot continue to just grow them by collisions because this stops at roughly millimeter sizes. So instead, planetesimals form via the gravitational collapse of particle clumps. So in order for this to work, we first need to concentrate our particles. And I might be a little bit biased here coming from Lund, but I would say that the favored mechanism for doing this is via the streaming instability. And I have some sketches just trying to easily explain how this works. So if you consider you have your star, you have your disk around it, and then if we start by thinking of a pebble, a solid particle, then it feels the gravitational force to the star and it rotates with a Keplerian velocity. So all fine and well. Then if we instead look at the gas in the disk, now we feel the additional pressure force outwards from the star, and we thus rotate at a sub-Keplerian velocity. So if we look at these two together, then we find that the particle rotates faster than the gas, orbits faster, meaning that it will feel a drag force and thus start to drift towards the star. So this is what is known as radial drift. This is why pebbles always drift towards the star in such a disk. But here we only took into account the effect of the gas on the particle. And in the streaming instability, what you do is you take into account the effect of the particle on the gas. And if you just have a single particle, like in this sketch here, well, nothing much will happen. But if you have a collection of particles, then these will push on the gas in front of them, increase the velocity of the gas, which then leads to a smaller drag force and a smaller drift. And this means that the particles, which are sort of from further out and more isolated, they will be able to catch up, which then leads to even bigger collections of particles, which pushes more on the gas. And this is a runaway process, which eventually leads to the formation of dense filaments. So here you can see a filament forming in a streaming instability simulation. And these filaments can then gravitational collapse to form your planetesimals. So this was sort of a sketch, so we can also look at a simulation of how this is going on. So this is one of the more recent and high resolution simulations of this process by Rix and Lee from the US. So here in the beginning, there are already some filaments forming. And then as one turns on the simulation, you can see how these filaments, they start to merge and they eventually gravitational collapse to form your planetesimals. So here we have the particle clumps, which are our planetesimals, basically. Okay, so in order to trigger this process, we typically need some density enhancement. So this plot here to the left by Lee et al. Shows for what metallicities or dust to gas ratios and Stokes number, which you can think of as a proxy for the particle size, that this streaming instability is forming filaments. So the green curve is the most recent one. And most particles, millimeter particles, are typically of a Stokes number of less than 10 to the minus 2. So we're in this regime. And this means that this green curve here is above 1%. So it's not enough just to have our sort of initial dust to gas ratio in the disk, but we need to somehow enhance it. Now, here they've also shown that you can actually have lower than this, the metallicity, if the particles are large enough. However, you should take this map with a little bit of grain of salt, because this does not include, for example, turbulence. Because if you have turbulence, it will stir up the dust layer, and then it's harder to sediment and form clumps. And in my work, I will have used this orange curve here by Young et al., which was the sort of most up-to-date condition we had when I started this project. But in the region with small particles, you can see there's basically no difference here. So that's fine. Okay, so that was basically the sort of general introduction. So then we can move on to the specific topic of this talk, which is this planetesimal formation at gap edges. So the motivation behind this work comes from these observations of protoplanetary disks. So here you see a selection of disks from the D-sharp survey. So what you see here is basically the millimeter or pebble-sized particles in these disks. And they're very different, but one thing that most of them have in common is that you have these ring and gap features in the disk. And there are many different explanations for why you can form such features, but one of the favorite ones is that they're formed by planet-disk interactions. So there's another tiny little sketch. So basically, if we consider a case with no planet in the disk, then we have the left case here. Then, we have your surface density profile. It's fairly smooth. And a particle in this disk, it will start small, grow with time, reach millimeter size roughly, and then start to drift towards the star. And unless something else happens, it's lost to the star. So boring. However, if you have a massive planet in the disk, it's going to open up a deep gap. And at the corresponding gap edge here, there will be a pressure maxima. And when there is a pressure maxima, the pressure gradient is 0, meaning that this drift of particles is stopped. It's halted. So particles become trapped here. So now the particles will grow, reach the point and become trapped. And with time, you just drift more and more particles into this location, meaning that the density becomes high, and then thus making this a favorable location for planetesimal formation. So this process of planetesimal formation at gap edges has then been the topic of what I've worked on. And there are a few questions that we can ask ourselves here. So the first question is fairly easy, is just, does this process work? Do we actually form planetesimals here? So that's the first thing we wanted to answer. The second thing is, what is the effect on disk evolution? So does this process actually make a difference to what we see, for example, in observations? And then we also want to ask ourselves, what is the fate of these planetesimals once they're formed? And you can split this up into several questions. For example, like, where do they end up? And also, like, does any of them actually accrete onto the planets and thus partake in the planet formation process in some way? Okay, so we started studying this process using just 1D global models. So we consider our viscous evolution disk, and then here we place 3 planets in the disk. And we chose to place them at the locations of the major gaps in the HL tau disk, which is sort of the most common example of a protoplanetary disk. So that would be at roughly 10, 30, and 80 AU in this case. And here you see the gaps in the surface density profile. So this is normalized gas surface density. So we have our 3 gaps, and here I also show the pressure gradient in the disk. And here we have used rather massive planets so that we're definitely trapping the particles. So if we would have a pressure gradient of exactly 0 here, then we're at what we call the pebble isolation mass. So that's when we're just massive enough to create a gap deep enough to trap particles. But now we have rather massive planets. Okay, so that's it for the planets. Then for the particles, so we have 100,000 particles per simulations, or I should say superparticles. And for the physics of particles, we include both gas drag, stirring via turbulent diffusion, and coagulation, so collisional growth, basically. And we use the scheme here for Göttler et al. So here I will show you how this system evolves, and I will start by showing you how it evolves when we do not include planetesimal formation. So here it's just the particle size and then the image axis. And then as we turn on the simulation, we form 1 millimeter particles, just like before. But now we can see that we also start to pile up a lot of particles at the gap edges. So here we have very high densities. So then this is where we expect to form our planetesimals. Now we can see that at the innermost planet gap edge here, we do see some pileup, but not as much. And this is because here we can actually transport some particles across the gap because of this turbulent diffusion. Okay, but that's without the planetesimals. So then we can add them and see the difference. So we use these conditions from Young et al. From the streaming instability. And we further take this map here and scale it linearly with the pressure gradient, because it has been shown that the streaming instability is more efficient when the pressure gradient is low. So basically, as we approach the gap edge, it gets easier and easier to form planetesimals. And it should be said that when the pressure gradient is exactly 0, there is no radial drift. So basically, there is no streaming instability. But in this case, we would just form our planetesimals by gravitational instability instead. But taken together, these conditions basically represent an upper limit on the amount of planetesimal formation in this system. Also because we still do not have any turbulence used in this map here, for example. So then I will show you how the particles evolve in this system. And here in the top plot, you'll also see how much planetesimals that form in Earth masses and at what locations in the disk. So if I turn on this then, we see that we very quickly begin to form a lot of planetesimals at the gap edges, but basically nothing in between. And we also see that we quickly deplete this region interior of the planets, because now, and you see, we no longer have these big pileups of particles anymore, because basically now they're all turned into planetesimals. So in this simulation, we form like almost 300 Earth masses. Now, this really is an upper limit. I do not expect us to form that much. But even if we would only form like 10% of that in reality, that's still quite a lot. So that's still very significant. Yeah. No, there is no gravitational n-body in these simulations. So what we do in practice is that at each time step, we sort of look in the grid cells, then we see, okay, how many planetesimals are there here and so on, or particles. Then we check this like dust to gas ratio, the average size. And if we sort of reach this green region here, we basically take one particle, just turn it into a planetesimal. And then we just leave it where it forms. The simulation doesn't care about it anymore after that, so to say. So that part will come later, so to say. Okay, but this is just sort of what I call the nominal simulation. We also did a lot of different ones. So for example, here we varied the planet mass and we varied like the alpha values and so on. But what we see is that regardless of which parameters we choose here, we always get some planetesimal formation. So basically the conclusion here was that we appear to get significant planetesimal formation at the gap edges. And this is also sort of in line with what others people have found in sort of similar studies. Okay, so that's basically our answer to the first question. And then we can move on and look at the effect on disk evolution. So here I show some snapshots of the solid to gas surface density ratio. And initially early on, we basically have a 1%. And then as time goes on, we get less and less. And basically, we could see it already in this plot here. We basically deplete the inner disk. And I should also say that here I split this into a dust plus pebble component and a planetesimal component. And the one we're interested in is only the dust and pebble component here, because that's what we would be able to see in some observations. Now, for the sake of easier visualization, I also took the sort of 1D data here and made them into some symmetric 2D images. So then you get this. And here it gets even clearer that we basically deplete the inner region. And in case there are any observers here, I should also like just point out, these are not synthetic observations. There's always someone to ask that. It's just the solid to gas surface density ratio. So you can use this to get a feeling for how the disk looks like, but you cannot actually compare it to the observations, because then you need to also care about opacities, resolution of ALMA and stuff like that. Okay, but what we see here is basically what happens when we have the upper limit on planetesimal formation. So the opposite case would be if we don't have any planetesimal formation at all. So that's the sort of bottom row here. And then you instead get these very bright rings of dust and pebbles, and also some pebbles in the inner disk. So in reality, we're going to be somewhere in between these cases. So here's just an example of that. And where that is depends on the efficiency of planetesimal formation. So basically, how much of the dust and pebbles in the ring do you convert into planetesimals? And that is something which is very unknown at this point. And it is something that I'm hoping to sort of answer in the future, because it obviously has a big effect on like how the system evolves. But in order to do that, you cannot use these sort of 1D simulations. You actually need to go 3D hydro for this. And since I'm anyway talking about sort of what is missing, what are the uncertainties here, I wanted to mention two other things which one would need to improve on in order to make these simulations here become even more like reality. And the first thing is particle filtration across gaps, because this is something that people have studied a lot in like 1D and 2D. So here are some examples of this with very different results, actually, depending on the studies. But no one has really looked at this properly in 3D with a planet. So this is something that we would need to look into. And another thing which people quite often forget is also fragmentation at gap edges, because it has been shown by, for example, studies by Jana Draskowska, that if you have a pressure bump and you pile up a lot of particles here, then at some point fragmentation can become so efficient that you start to get a tail of small particles, which can then make it cross the gap and thus sort of leak particles from the bump in that way. So if you want to properly model a system like this, you actually need to take all of these effects into account. Okay, and before I move on to the next topic, I just wanted to say that, well, this is the nominal simulation, but yeah, we did a lot of other simulations. So here are just some examples of how things can look at when we vary the parameters. So for example, if we lower the planetary mass, we find that we no longer completely deplete the gaps of dust and particles, but to get some more like small enhancements and depletions instead. Okay. Yes. This one? Oh, this one? One before. This one? Yeah. Yeah. So if you use ALMA, what you basically use is millimeter wavelengths. So what then you will be able to see is roughly millimeter sized particles. So that's the light from those particles that you will see. So if you look at ALMA images, what you see there is those kind of particles, and exactly the particle, the size depends on the wavelength of the observation sun, but you will never be able to see the planetesimals. Basically, the only way we have to infer planetesimals in a disk is to look at sort of the debris disk that you get when they collide. So if planetesimals collide, they will create dust, and then maybe we can see that dust. But that's the only way we have to detect those. So we cannot detect them directly, basically. Okay, but then now we looked at the formation. So now we can move on to the next step, which is the fate of them. So what actually happens to all these planetesimals that form at the gap edges? And we wanted to start by just answering the question, where did they end up? And we use this now we do this using n-body simulations. And we wanted to start very simple. So we just consider a case when we have no disk evolution and we have planets with constant mass and no migration. And then we form all the planetesimals at the gap edges in the beginning of the simulation, and we start them with a roughly 0 eccentricity. So here you have some snapshots of eccentricity versus image axis. So we have our free HL tau-like planets again, and then initially all the planetesimals are sort of at 0 eccentricity at the gap edges. And then what we see is that the close proximity to the planets result in fast scattering, and they basically spread out the planetesimals across the disk very fast. So already after 50,000 years, they're basically all over the disk. So the main takeaway here is really that these planetesimals formed at gap edges do not remain at their birth locations, but they spread out all over the place. And this depends a little bit on where you form them. So here we form them very close to the planets, even inside of the feeding zone. But also if we take them outside of the feeding zone at like 4 to 5 Hill radii from the planets, the result is the same. And it's only if we place them at like 6, 7 Hill radii from the planet that the scattering is actually so slow that we can keep some planetesimals where they form until the end of the simulation. So it seems that this scattering is pretty robust. And then if we look with more sort of details on this plot, we see that we actually get quite a lot of planetesimals with high eccentricities in the inner part of the disk. So here the gas density is pretty high, meaning that these are likely to suffer from surface ablation. So this is a process where the frictional heating of the gas heats up the surface of the planetesimal and leads to vaporization of volatile ices there. So basically it results in mass loss. So we lose both gas, but also solid grains which are entrained within the ice. And some of this gas will eventually recondense to form ices once again. Okay, so we decided to add this process of ablation to our simulations. So here is how it looks like then. And now the color coding here of the planetesimals is the surface temperature of them. And now the planets in HL tau are pretty far away from the stars, or the assumed planets in HL tau. So this means that it's only really the innermost planetesimals, like the ones around here, that obtain high enough temperatures to be efficiently ablated. And if we look at how much we ablate, then in what I call the nominal simulations, that will be here, this blue line, we see that towards the end of the simulation, we have lost like 10% of our total mass because of this process. However, this depends extremely much on the density of the disk. So if we consider, for example, a disk with 10 times less density, so a much older system, then we're at like a few percent and can basically neglect it. And we can look at also where this ablation occurs, and it's mostly interior the innermost planet. So this is where we lose our mass, basically. Okay, but the HL tau planets are pretty far out. So if we instead switch to consider like our solar system, then if we look at Jupiter and Saturn, these are both massive planets which would have opened deep gaps when they form, and thus likely have had planetesimals forming at their gap edges. And since these planets are much closer to the star, it means that the density where the planetesimals form is higher, meaning that they will get higher surface temperatures and thus experience more ablation. So here I show sort of a similar simulation, but now we have Jupiter and Saturn instead at the current positions, and we once again form planetesimals at the gap edges. And just like before, they scattered, they distribute, but now you can see that the temperatures are much higher here. And in this case, the addition of ablation actually makes a significant difference to the no ablation case, which you can see in the next plots here. So here in the top panel, we have the with ablation case, so to say, and in the bottom, we had no ablation. And here I also extended the temperature scale, you can see. So if we compare these two, then first of all, we see that if we don't have ablation, the planetesimals get much higher surface temperatures. And this is because we no longer have any cooling due to the ablation process. And we also see that we now have a population of planetesimals in the inner disk here, which we do not at all have in the top plot here. And these are basically circularized planetesimals, so planetesimals which are experience the gas drag and get circularized. And we do not have them up here at all because basically the planetesimals are ablated before this can happen. Okay. And in the solar system, then we also get, as I said, significantly more ablation. So in this case, the nominal simulation will lose like 70% of its mass because of this process. However, if we then once again consider an older disk with 10 times less mass, then we're down at like 20%. And if we look at where ablation occurs, it's mostly either just interior of Jupiter or just exterior of it. So then if we want to, we can take it one step further and ask basically what happens to all of this mass, which is ablated. And basically a large fraction of these vaporized ices will eventually recondense to form solid ice once again. If we assume that all these solid ice would just coagulate to form new pebbles in the disk midplane, it means that we get a new flux of pebbles. So here to the right, I've sort of estimated the size of this pebble flux and also the corresponding pebble to gas density. And the interesting part is that this flux is now either interior of Jupiter or in between the planets. So this is the regions where usually before was emptied of pebbles because all the pebbles stop at the gap edge. So this means that we get some sort of transport of pebbles across planetary gaps. So it's not just enough, if you have a massive disk, to sort of drop a big planet in there and expect all the pebbles to stop at the outside and these disks to have sort of components that don't mix. Because this process of scattering ablation will actually deliver material to the interior of the disk anyway. And the reason it's also interesting is because a lot of people actually claim that this is the case. You put a Jupiter in there and then you split the disk, but it's not as easy as that. Okay, so then the sort of final things looked into was the accretion onto the planets. So why do we care about this? Well, this is because if you look at, for example, Jupiter and Saturn, they're estimated to have somewhere like 20 or more Earth masses of heavy elements in them. And if you look at exogiants, then you find that this estimate is somewhere like 10 to 100 Earth masses. So this is an example from the Tungle plot where you see that. So basically that is way too much heavy metals to just put into the core of the planet, meaning that giant planets seem to typically have atmospheres which are enriched in heavy elements. And then you need some way of explaining this. And a common explanation is to say that these planets are accreting planetesimals during the gas accretion phase. So then you basically add the metals to the atmosphere afterwards. And there are many studies of this process, some from this group, for example. And typically a lot of them, they assume that you have a massive wide stretch disk of planetesimals. So you basically have planetesimals forming everywhere. But in our simulations, we show that, okay, maybe the planetesimals instead form at specific locations, such as the gap edges. So we wanted to see how efficient is the accretion of planetesimals in this case. And this is the collaboration that I did also with, for example, Ravit and also Claudio Valletta. So the way we studied this is we continue to use our n-body simulations, but now we want to use a more advanced model. So we sort of include disk evolution. And now we also consider the formation of the planets by both gas accretion and migration. And the first thing to know about gas accretion is that it's very unconstrained. So if you look in the literature, you found a plethora of different prescriptions, which are like completely different. So we just picked two very different ones here and wanted to sort of compare these cases. And then when we do this gas accretion and migration, we find that if we look at Jupiter and Saturn, which is what we focus on now, then Saturn basically needs to start accreting gas later. But we don't want to just sort of drop in Saturn into the simulation halfway through. So for that reason, we also add some core formation to Saturn. And the growth tracks that we use, you can see down here in the bottom left plot. So we have planet mass versus same major axis. And the dashed line here is the pebble isolation mass. So that's when core formation stops and gas accretion initiates. And in what I call scheme 1, the blue scheme, so if we look at Saturn, we can see that we start accreting some pebbles here. Then we reach this pebble isolation mass and we start to accrete gas. And basically in this scheme, we do not migrate very far. But if we then take the other scheme, we have a longer attached phase for gas accretion. And then we see that we form further away from the star. We migrate quite far. Then we migrate also far during the attached phase. Then we reach what is known as runaway gas accretion until we reach a final mass. So basically in scheme 1, we migrate a short distance, and in scheme 2, we migrate a long distance. Okay. And then since we now want to look at the capture of planetesimals, we also want a proper description for the capture radius of the planet. And here we use this new prescription from Valletta et al. From last year. So basically here we have 3 regimes for the capture radius. So when we are forming the core, we don't have any gas envelope. So then the capture radius is just the physical radius, basically. So that's simple enough. Then when we're in the attached phase or enhanced envelope phase, they also call it, we have this very large extended gas envelope around the planet, which means that we have a very large capture radius. So we can capture planetesimals from far away, basically. But then when we reach runaway gas accretion, this envelope quickly contracts and we get a smaller capture radius again. Okay, so this is our 3 phases. And we can already now say that if we're going to accrete some planetesimals, then, well, we're most likely to do so during this enhanced envelope phase of gas accretion, because that's when the capture radius is the largest. Okay, and then for the planetesimals, now, unlike before, we just formed them all at the same time, we now form them continuously at the gap edge at the rate at which pebbles is drifting into it. And I should also say finally that now we actually remove the ablation. And this is partly because we form quite late in disk lifetime now, so it wouldn't be very efficient, but also because we find that the planetesimals which are accreted are so fairly quickly, meaning that they'll basically get accreted before they're ablated anyway, so it doesn't matter. Okay. And for the planetesimals, so before I just show you how they evolve, yeah. So the capture radius is understood, it's more based on like how extended the gas envelope is. So it's, so I'm not exactly sure how Claudio did when he calculated this in his paper, but basically during this first phase of gas accretion, the envelope is very sort of big and spread out. So that means that the planetesimals can come from quite far away and be affected by the gas here, the gas drag, and then it can sort of spiral in and be accreted onto the planets. While in the later phase, yes, the planet is more massive, so the Hill radius is larger, but this extended envelope is much more contracted with a higher density. So the planetesimals can come as close as before, but there is no gas there, so it will not get this spiral in effect and be accreted onto the planet. It has to get much closer, basically, for that to happen. So that's the reason. Okay, but let's look at the planetesimals. So there's 2 important assumptions we make, which I just wanted to point out. So the first one is that we say that no planetesimals form before the end of core formation. And the second one is that now we see that all pebbles reaching the gap edge are turned into planetesimals. And this has 2 implications. The first one is that we really get an upper limit on a planetesimal mass, because now we literally take like the entire pebble flux and just turn them into planetesimals. And the second one is that it means that once Saturn reaches pebble isolation mass, the pebble flux towards Jupiter will be completely halted, so then there will be no more planetesimals forming there. So basically, we first form planetesimals at Jupiter's gap edge, and then at Saturn's. And if we look at how this system evolves, there's eccentricity versus symmetry axis again. Then we see that we start forming our planetesimals at Jupiter, they get scattered, they distribute again, then we form them at Saturn, same thing happens. And then we remove the gas disk at 3 million years. And then you see that basically the inner disk region is clear of planetesimals, and the only ones which remain are in some sort of scattered disk beyond Saturn. Now, we do not include Uranus and Neptune here, so if we did that, that would also affect how these final planetesimals are situated. But that was just the dynamics. So what we're interested in was, of course, the accretion. Yeah. Mm-hmm. Yeah. So the assumption is not valid at all, in the sense that we don't expect the entire pebble flux to turn into planetesimals. However, the reason we do this is because then we get an upper limit. So then so that if we say then accrete 5 Earth masses, we know that that's the upper limit. We cannot accrete more because there literally isn't anything else to accrete. So that's why we make the assumption. In reality, we have no idea what this is because this depends on this efficiency of planetesimal formation, which is very, very unknown. So we don't know exactly what it would be, but this is the assumption. Yes. Mm-hmm. So we don't just remove it. So we actually have a photoevaporation rate, which sort of slowly removes it. But then towards the end, it will be faster and faster, basically anyway. So it's not just removed, but it's fairly quick. So if I look at the mass accretion rate onto the star, it will be something like this and then go relatively fast towards then. And we just picked 3 million years here because that's the typical disk lifetime, but we could have equally well put 4 million years in that sense if we wanted to. Okay. So here we then have the accretion. So in this case, we will form somewhere between 20 and 30 Earth masses of planetesimals at the gap edges. So that's what we have available now to accrete. And then in a bottom plot here, I show you the accreted planetesimal mass in Earth masses and the corresponding accretion efficiency, which is here calculated as a fraction of the total planetesimal mass in the system. And then blue here is onto Jupiter, and red is onto Saturn. And there are a bunch of different simulations here, but before we look at them, I just want to point out that the maximum accretion efficiency here is less than 10%, which corresponds to, in this case, roughly 3 Earth masses onto Jupiter and 2 onto Saturn. And this is despite the fact that we took all the pebbles and turned them into planetesimals. And here we also took all these planetesimals and placed them inside the feeding zone of the planet. So this already tells us that this is a very inefficient process because this is really like the maximum amount we can accrete, so to say. But then we can also look at how things vary, of course. So if we start by looking at the formation location, so if we form them inside the feeding zone, which here is like 2 to 3 hill radii, then yeah, we do accrete a little bit. But as soon as we place them outside, which is at 4 to 5 hill radii here, so still fairly close, we don't accrete anything, basically. So we can completely neglect this process. And we can understand a little bit of why that happens if we look at this part here. So here you have the capture radius again. And if you remember what I said before, so we basically have this enhanced envelope phase where we are expected to accrete a lot. And here in the top, I show the cumulative accreted planetesimal mass. And so these simulations here, for example, these lines here, these are when we form them inside the feeding zone, and these dots here is outside. So here we find that when we're in this enhanced envelope phase and we form them inside the feeding zone, we basically continuously accrete a fraction of the planetesimals that form. And then once we up here reach runaway gas accretion, we still accrete a little bit, but not that much. However, if we form them outside the feeding zone, we never get this continuous accretion of a fraction. Instead, we get more like just random accretion events. So this is why we don't accrete so much here. Okay, and then we can also compare like planetesimal sizes. So we tried like 100 kilometers, which is the sort of standard outcome of a streaming instability simulation. But we also tried like a radius of 10 kilometers and also down to 300 meters. And basically what we find is that there's basically no difference here. And when we first looked at this, it was a bit surprising because small planetesimals have a larger capture radius. So it's easier to accrete them in a way. So you would expect the 300-meter ones to be more accreted. But the reason they're not is because of their dynamics. So you can look at some plots here. So here shows snapshots of the evolution, dynamical evolution. And the blue dots here are for 10-kilometer planetesimals, and the red ones are for 300 meters. And basically what happens for the really small ones is that unless they're immediately accreted onto the planet, they'll be scattered and then quickly dampened by the gas drag, which puts them on orbits which are no longer Jupiter or Saturn crossing and sort of outside the feeding zone. So that is why we accrete less than normal if we use the 300-meter ones even. So that does not solve our problem, so to say. And then finally, we can also compare like our different gas accretion schemes. And basically, I will not go into too much details, but what we find is that if we have the shorter migration distance, we accrete less. And this is pretty consistent with what other people have found as well. So the conclusion here is really that it's hard to explain the high element content of these giant planets with this process because we simply accrete so little that in order to get like 10, 20 Earth masses, we would need to have like 100 or 200 Earth masses at the gap edges, which is not really super realistic. So how do we then solve this? What are the sort of alternative solutions? Well, there's, for example, the work by Shaw, where he showed that if you have this wide stretched disk of planetesimals and you let the planet migrate a long distance through it, then it can actually make it work in some cases. You can also look at the enrichment of pebbles, which are drifting inwards and evaporating. So basically, if a pebble drifts towards the star, then at some point it will pass through some ice lines, evaporate, and then enrich the gas in this region. And then the planet can just simply accrete this gas and automatically get some enriched envelope. So that is one process. And then, of course, we always have our giant impacts and mergers, which can just come in, smash into the planet, and enrich the atmosphere. So that also works. Okay. So then I can sort of summarize this saga of planetesimal formation so far. So basically what we found is that, yes, it looks like we could have some planetesimal formation at the gap edges. And this would then have major implications for the distribution of pebbles, and thus how this disk appear in observations. We looked at what happens to these planetesimals where they form, and we see that they do not remain where they form, but they're scattered all over the place. And if the disk is fairly young and massive, we can get some ablation in there, which transports material across the gaps. And we can also look at the accretion efficiency, and we find that basically they're not accreted onto the planets. So we cannot really use this process to explain enrichment of atmospheres. So this is what we sort of did so far. So this is how far the story saga has gone. But then we can also ask ourselves, okay, what's left here to discover? What's left to explore? I'm soon done. I have like 2 more slides. And then basically what we can continue to do here is we can try to answer these questions that we talked about during the talks. Basically, what is missing in this picture? And the first and really obvious one is that even though our work and others' work suggest that probably there is planetesimal formation at gap edges, this has not actually been confirmed in 3D hydro simulations. So no one has done this. So this is the first thing that someone really needs to do. And then there are also these other questions that we talked about, like what is the efficiency, what is the particle filtration, and where do they actually form? And the thing that all these processes have in common is that now you need sort of detailed 3D hydro simulations of particle gas interactions and a planet in there in order to look and answer these questions. So this is what we are sort of starting to work on now. This is a collaboration with Xiaoqun Yang, who is now a lecturer at the University of Alabama. And well, all projects have its challenges. I figured I'd just say a word about this sort of main challenge in this project, which would be the size of this simulation. So before we sort of did a global 1D simulation, but now we need to sort of zoom in on the ring here. And here I just show an example of this setup in 2D. So here you have you have the gas and you see your horseshoe orbit around the planet. And here we have the dust. And I picked a very low mass planet here. So you can see some enhancement, but not much. But the size of the simulation is the interesting part, because a normal streaming is the simulation, like the one from Yang et al., have a box with a side of 0.2 scale heights. So that's a normal standard streaming instability simulation. Now, this year, earlier, there was a simulation by Carrera and Simon where they took such a box and then placed an artificial pressure bump in there. And then they had a very large box for a streaming instability simulation, which is 9 gas scale heights in radial direction, and then 0.2 and 0.8 in Y and Z. So this is a very large box. It took a long time to run and so on. But now in this work, we don't only need an artificial pressure bump, but we need to fit the entire gap edge. So here is a plot from Yang and Su, where they have the shape of the gap in such a simulation in the 2D setup. And here we see that if we want to fit the entire gap, the edge, and we also need a bit extra to get the boundary region, we probably need like a radial side of like 16 scale heights. And now, because we can't just put in it there and like artificially make the pressure bump be stable, we also need to somehow like resolve this entire horseshoe orbit here. So we probably need at least as big in the Y direction as well, and probably twice as big. So that's like 32 scale heights. And we also cannot have a super like narrow Z direction, because the planet's gravity will act to sort of puff up the particles at the gap edges and then like distribute a layer. So worst case scenario, we need like 4 scale heights here. So then we can already see that this box is going to be very big, meaning basically that these simulations will take a very long time when we hopefully get them to work. So that's the sort of major challenge here. But this is what we're working on at the moment, and hopefully not the too distant future, we'll be able to use these simulations to answer some of those questions that I posed before. And that was the end of this talk. So thank you for listening.